So we were talking about the sequences last time. We started chapter 9, but we didn't finish this section of sequence in section 1. So a sequence is a set of infinitely many numbers in order. So you have infinitely many numbers, and they are in order. You cannot swap the order of the numbers. Sometimes you might need to, recognize the pattern for a sequence. We talk about the limit of sequence. For example, we talk about different things about sequence. How to write explicitly the terms of sequence if the format of a sequence is given. Okay, but sometimes the problem is on the other way. Okay, so you are given a sequence limited by and listed by numbers, but you're trying to find the format for the sequence and try to find the limit for the sequence. For example, in this example, we want to find the limit of the sequence of an which start from 201 and then 403, 805, 17, 1607, 3209. I think we did this example before. Okay, so I'm not going to repeat it. All right. Okay, the next topic is about the monotonic sequences and the bounded sequences. Monotonic sequence means the sequences are always non-decreasing or non-increasing. Okay, so they non-decreasing means they either increase or equal. Okay, so they're not decreasing from the current term to the next term. Is not decreasing. It could increase or could be the same. And it's always like this for the whole sequence. Okay, so if I write the inequality for the terms in the sequence of an, for example, so a sequence is non-decreasing if a1 is less than equal to a2 or less than equal to a3 and so on. So this is non-decreasing because it's increasing or equal. Okay, if we plot the sequence in the graph, and then you can see the dots either going up or keep the same. So on the left side below the graph, and then that's called monotonic. Okay, so it doesn't fluctuate. And another case is called a sequence non-increasing. Okay, so it could decrease or could keep the same. Rather, inequalities will be a1 greater than equal to a2, greater than equal to a3, and so on. So it goes down basically. And if you plot the sequence in the graph, it's just like the graph on the right below. All right. So that's those two cases are kind of monotonic. It's either increasing or decreasing, basically, for all the terms. Okay. So sometimes you want to know whether a sequence is monotonic or not. And that is an important property actually. So let's just see some examples of sequences in problem A. An equals 3 plus -1 to the n. And this is the example we did before in the beginning of this section. So if you write the terms of the sequence explicitly, they are like 2, 4, 2, 4, 2, 4, and so on. If n is even, then you're going to get the -1 to the n to be positive, so you get a 4. When n is odd, then -1 to the n will be -1, so you get a 3 minus 1, you get 2. So that's why you get the 2 and the 4 back and forth fluctuating. So this is not monotonic, okay? It fluctuates. It doesn't keep growing or keep decreasing, okay? In example B, we got another sequence Bn equals 2n over 1 plus n. In order to know whether the sequence is monotonic or not, we have to rewrite this sequence, the general formula for the sequence in a different format. So what we do is we divide both the numerator and the denominator by n. And then you get a 2n over n on the top, and that is 4. That is 2. And if you divide 1 plus n in the denominator by n, then you can break up into two terms, which are 1 over n plus n over n. Okay, by using the same denominator. And then n over n is just 1. So at the end, we get a 2 over 1 over n plus 1. And then we have one term in this expression that depends on n. And that's why we need to rewrite this sequence. Previously, we have both n on the top and at the bottom. So it's hard to determine whether the sequence is increasing or decreasing. But once you write in the format only with one term in this expression depending on n, then we can judge whether the sequence is monotonic or not. So what we do is we just let n increase. So as n increases, 1 over n decreases. Okay, I'm sorry. Why did I write increasing here? Okay, so 1 over n decreases. Okay, if we flip it. So so then what? So 1 over n plus 1 also decreases. Okay, you just add 1 to each term, so that doesn't change the tendency of the sequence. And then 2 over 1 over n plus 1, so you put this 1 over n plus 1 in the denominator, then that should increase. Okay, that should increase. So the sequence actually increases, not decrease. I'm sorry. Yeah, I got it wrong here. So this is indeed a monotonic sequence. Okay, it is an increasing sequence. Okay. In problem C, that's also an example we did before at the start of this the section. Cn equals n squared over 2 to the n minus 1. So this one is a little tricky, because we have both n squared on the top and the 2 to the n in the denominator, and they're both in, so you don't know what happens to the quotient of these two. So let's just try to write the first few terms and see whether there's a tendency for increasing or decreasing. So when n equals 1, you plug in 1 for n, you get 1 squared on the top and the 2 to the 1 minus 1 at the bottom. So that will be 1 over 1, which is 1. So that's C1. And for C2, just plug in 2 for n. So you get 2 squared on the top and the 2 squared minus 1 at the bottom. Okay. 2 squared is 4, so you get the 4 over 3. So that's C2. And C3, if 3 for n, so you get the 3 squared on the top and 2 to the cube minus 1 at the bottom. 3 squared is 9, 2 cubed is 8, 8 minus 1 is 7. So we get 9 over 7 for C3. C4 will be 4 squared over 2 to the 4 minus 1. So that'll be 16 over 16 minus 1, which is 15. So we got the 16 over 15 for C4. So then you try to compare those numbers, see if they are monotonic. And you see they're not. It's easy to check that one is less than 4 over 3, obviously, and that's also less than 9 over 7. Okay. And then you got 16 or 15, which is smaller. So 9 over 7 is actually greater than 16 over 15. So the sequence increases initially, but then start to decrease at C4. So the sequence is not monotonic. It has some fluctuation. Okay. So that's C4. That's the third example. Any questions? Okay, so that's monotonic sequences. And let's see, I guess. Let's talk about bounded sequences now. Bounded sequences are a different topic here. So what is meant by, you know, a sequence is bounded? And we have different situations in here, as you can see from the three graphs below. In the first case, if I plot all the sequences with the dots, you can see all of the points are above some horizontal line. So we call this sequence is bounded above. So it's bounded above by some number m. Okay. So a sequence an is bounded above if an is less than or equal to m for all the n, so all the terms in the sequence. And this number m is called the upper bound for the sequence. Okay, that horizontal line. Okay, so that's the left graph. And then obviously you can talk about the bounded below in the graph in the middle. So all the points of the sequence are above some horizontal line. So this is called bounded below. There is a bound below. Okay. So a sequence a bounded below if an is greater than or equal to n for all in all the terms. And n, the number in the horizontal line in the middle graph, is called the lower bound for the sequence. Okay. So that's the lower bound. Everything is above it. And then we have another term, bounded. Okay. So we talk about bounded above and below. And what is meant by a sequence is bounded. It means it's both bounded above and bounded below, like in in the graph on the right. So if you look at the red points, the sequence plotted in the graph, then you can have a upper bound horizontal line on the top and the lower bound a horizontal line below, and all the points, red points, are between those two horizontal lines or bounds. Okay, so that's called bounded. So it's bounded both above and below. Okay, so a sequence an is bounded if an is both bounded above and bounded below. Okay, so these are some definitions for the boundaries of sequence. All right. So let's do some examples about this boundaries. Okay, so we have some terminology here. You can always find the smallest upper bound of a sequence, and that's called the least upper bound of the sequence, and denoted by LUB, least upper bound. Okay, so you have different, upper bounds. You can always find the upper bound of a sequence if a sequence is bounded above, and you can find the smallest upper bound. Okay, you can always find the smallest upper bound, and that's got the least upper bound, and denoted by LUB. Okay, let's look at one example and see what it means by this least upper bound. Okay, so we have sequence 1/2, 2/3, 3/4, 4/5, and so on. So the general formula for this sequence is n over n plus 1. Okay. So obviously n over n plus 1 is less than n plus 1 over n plus 1. Okay. Because you're adding 1 in the numerator and you make the number larger. But n plus 1 over n plus 1 is 1. So that means all the n's, all the terms in the sequence is less than 1. So 1 is the upper bound for the sequence. You can see the horizontal line in the graph on the right, and all the points of the sequence are plotted or below this horizontal line. So this horizontal line is the upper bound for this sequence. So that is 1. And you can also check this is actually the least upper bound for this sequence. You cannot find any other bound below this horizontal line. Okay, so to see that, let's just try to find the distance between the upper bound 1 and the terms of an. So 1 minus an, if you do that, that's 1 minus 1, n over n plus 1. So you can rewrite 1 as n plus 1 over n plus 1, and then you subtract the numerator and keep the same denominator. So you get the n plus 1 minus n, which is 1 on the top, and the n plus 1 at the bottom. So when n it becomes large, yeah, this n plus 1 becomes large, so the whole thing over of 1 over n plus 1 becomes smaller. So especially when n approaches infinity, then 1 over n plus 1 approaches 0. So that means the difference between the upper bound and the terms becomes extremely small, approaching 0. There is a limit for this difference between the upper bound and the terms. Okay, so you cannot have any other horizontal lines below 1, which is also upper bound for the sequence, because distance between the upper bound and the terms of the sequence is approaches 0. So that means there is no upper bound less than 1. So 1 is the least upper bound of the sequence. Okay. Any questions? Let's do the next page. All right. There is a very important theorem for the boundaries and monotonic sequences. Okay. It says if a sequence an is bounded and monotonic, they converge. Okay. So what does it mean? If you have a sequence bounded, okay, so that means bounded both above and below. Okay. All the terms of the sequence are between two bounds. Okay. One on the top and one at the bottom. And then the sequence is monotonic. Okay, so it's either increasing or either decreasing. Then all the terms of the sequence will approach a limit. That's what it means by converge. Okay, all the terms of the sequence will have a limit as n approaches infinity. Okay, like in the graph. Okay, so let's do one example. So the sequence we have here is an equals 1 over n. So let's see whether this sequence is bounded and monotonic. Okay. As always, we're talking about n greater than equal to 1. Okay. If we do not specify what n is, it starts from 1 automatically. So that means if you take the reciprocal, 1 of n will be less than equal to 1, right? But n itself is positive. It's a natural number, so it'll be positive. So 1 over n is also positive. So that means 1 over n is greater than 0 and less than equal to 1. So n is bounded. So it has a lower bound 0 and upper bound 1. Okay, so it's sandwiched between those two numbers. And also we can easily find the sequence is also monotonic, because when n increases, 1 over n decreases. Okay, you flip it, you get the opposite tendency. And so the sequence is also monotonic. It's decreasing. So from the theorem 9.5, the sequence converges. Okay. And you can actually see the sequence converges to 0. 1 over n has a limit of 0 as n approaches infinity. So that means it converges to 0. And it can be easily found from the graph, on the right, all the red points or the terms of the sequence, they just become smaller and smaller and approach the horizontal line. Okay, so that's the theorem. Let's do some more examples. In the next example, the sequence Bn is n squared over n plus 1. And we can claim this sequence diverges. So that means it does not have a limit. Okay, and you can easily see we got n squared on the top. So when n becomes large, this n squared becomes very large, and at the bottom we got n plus 1 also increases, but not as fast as the top. So the whole thing, if you divide n squared by n plus 1, it still gets larger and larger, and it doesn't have a limit. Okay. So to show that, you can also write the Bn, which is n squared over n plus 1 as two terms. So you can write the numerator n squared as n squared minus 1 plus 1, and then break up into two terms, by n squared minus 1 over n plus 1 plus 1 over n plus 1. Okay. And n squared minus 1 over n plus 1, you can factor the top and then cross n plus 1, and you're left with n minus 1. And then you add 1 over n plus 1. So obviously that's greater than n minus 1, okay? Because the term of 1 over n plus 1 is positive. So this Bn is always greater than n minus 1. So as n increases, this Bn does not have a limit. It's also keep increasing. So it is unbounded, okay? It's unbounded. So it diverges, all right? In the next example, Cn, we got -1 to the n. So this time it's pretty simple because you're gonna get the term to be -1 when n is odd. So for example, when n is equal to 1, then we get -1 to the 1 as the first term, which is -1. And when n is equal to 2, you get the second term as -1 squared, which is 1. So we get 1 for the second term. And then in the third term, n equals 3, so -1 to the cube, which is -1 again. And when n equals 4, you get the fourth term as -1 to the fourth, which is positive. So again, this sequence just fluctuates. So it's not monotonic. So it diverges. Okay, it doesn't have a limit. So this is the end of this section 1. So we talk about the different aspects of a sequence. Any questions about this section? If you don't have any more questions, I'm going to start the new section, section 2. Okay, we're going to talk about a different thing in section 2. Section 2, we call this section series and convergence. Okay, series is a different concept from sequence. So we talk about the sequence in section 1. So then what does it mean by series or infinite series? You just add all the numbers in the sequence and you call that a series. So that's the difference. A sequence is infinitely many numbers in order, and a series is the sum of those numbers. So that's the definition of series or infinite series, because you have infinite number of numbers to add. So in the notation of sigma notation, it's just like this. Okay, so you can write sigma n equals 1 to infinity of an. That means you add all the sequence of an, and that gives you the infinite sum, and that's called the infinite series. All right. So we are going to use the two sequence to study the series, and the way to do it is to define a sequence based on partial sums of the original sequence. Okay, so we have a sequence an to start, and then we're going to define a new sequence Sn. Okay, and we call this partial sum sequence, or sequence of partial sums of an. What's the new sequence? The first term of the new sequence S1 is just the A1, the same as the original sequence AN. And the second term of this new sequence is just the sum of the first two terms of the original sequence AN. So that's A1 plus A2. And the third term of the new sequence is just the sum of the first three terms of the original sequence. So S3 equals A1 plus A2 plus A3, and so on. So in general, the nth term of the new sequence, n, is just the sum of the first n terms of the original sequence, an. So S of n equals A1 plus A2 plus A3 plus A4, and so on, up to an. So that gives you the term of new sequence, Sn, or S sub n. So we obtain a sequence S sub n, and this sequence S sub n is called the nth partial sum of an. All right? Okay. So then we can just consider the sequence Sn. So what can you see is if the sequence Sn converges to a number S. Okay. So what it means by that? It means when n approaches infinity, then Sn will be approaching the total sum of all the terms in Sn, right? Because Sn is the sum of the first n terms of the original sequence An. So if n approaches infinity, that means you try to add all the terms in An. So if you get a finite number, so that means that's what it means by converge to a number is. Then the series converges. Okay, we call the series converges if the infinite series, if the sum of the infinite many terms of the an is a finite number, then we call the series converges. Okay, if you add the infinite many numbers of a sequence and you get a finite number, then you call this series converges. Okay, and S is called the sum of the series. That's obvious. That's what we do, right? All right, so let's do some simple examples and see how we can find the sum of infinitely many numbers of a sequence. So in the first example, we have a sequence of 1 over 2 to the n. So we try to add the sum of all these all the terms of this sequence. So we call this a series, as we already said. So just to list all the terms of this sequence, we get 1 over 2 as the first term when n equals 1. When n equals 2, we get a 1 over 2 squared, so that's 1 over 4. That's the second term of the sequence. And when n equals 3, we got the 1 over 2 to the cube, so which is 1 over 8. So that's the third term of the sequence. And when n equals 4, we got 1 over 2 to the 4, which is 1 over 16 as the fourth term of the sequence. And then we try to add those numbers, all the numbers in this sequence. And we see what the sum is. Okay, so we can just check the partial sums. As you know, the partial sum means you just add the finite number of terms, the first few terms we defined on the last page. So that's called the partial sum series sequence. Okay, and we use the S of n to denote it. So for example, in this problem, S1 is just the A1. That's just the first term of the original sequence. So that's just the 1/2. And we can rewrite this 1/2 as 2 to the 1 minus 1 over 2 to the 1. Okay. And the second term of partial sum is just the sum of the first two terms of the original sequence. So that's just the 1/2 plus 1/4. And you rewrite the 1/2 as 2 over 4, and then you add the numerators, you get 3. So the whole thing is 3 over 4, and we can rewrite it as 2 squared minus 1 for 3, 2 squared for 4 in the denominator. Okay. And you can do the same for the S3, the partial sum, the third term of the partial sum. By definition, is just the sum of the first 3 terms in the original sequence. So we get 1/2 plus 1/4 plus 1/8. And this time we got the least common denominator 8 for the 3 terms. So we can rewrite all the terms by using this least common denominator. So we get 4 over 8 from 1/2, and 2 over 8 from 1/4, and then we just add all the numerators. We got the 4 plus 2 plus 1, we got 7, and so the answer is 7 over 8, and we can rewrite it as 2 cubed minus 1 over 2 cubed for 7 over 8. So in general, you can see the pattern of the partial sums. If you add the first n terms of the original sequence of 1 over 2 to the n, you got Sn, so that will be equal to, why did I write 2 equal signs? Okay, so you can see that will be 2 to the n minus 1 over 2 to the n. Okay, if you look at the patterns of the answer in each term, it's just the 2 to the n minus 1 over 2 to the n. We have written all the results in this way. So when you take the limit of this S of n, you get S of n, you get 2 to the n minus 1 over 2 to the n, and then obviously you can break up into 2 terms from the denominator to get 2 to the n over 2 to the n minus 1 over 2 to the n. But 2 to the n over 2 to the n is just 1, so you get 1 minus 1 over 2 to the n. But when n approaches infinity, you get a 2 to the n also becomes large, approaching infinity. And so the limit of 1 over 2 to the n is just 0. So 1 minus 0 is 1. So the limit of this Sn is 1. But this limit is of Sn is just the total sum of the series, as we say. You take the limit of the partial sum, you get the whole sum of the whole series, of the whole sequence, right? And this result can be easily understood by the graph on the right. Okay, so we have a unit square in here. Each side has a unit length. So now, if you look at the half on the left, the area of that half piece is just 1/2, isn't it? Okay, the left piece. So we got that part, and then next you look at the lower right part. It has it's just 1/2 of the left piece. So the area of this part is 1/4. Okay, and then you keep on look at the part on the right, on the top and on the right of the left piece. You get 1/8 as the area. Okay, so then you just keep on doing this. Every time you add a piece with the area 1/2 of the previous term. Okay, so then we just use a geometry or area to represent this sum, this series. Remember, the series 1/2 plus 1/4 plus 1/8 plus 1/15, and you can represent this sum by a bunch of rectangles and add the area of each rectangle, and then you can see. So you're going to add those pieces and the blue pieces, and then you just keep on adding and adding, and at the end, what is left not filled by the color is just a small rectangle or square. But you keep on adding it, then eventually you're going to fill the whole unit square, and you get the area to be 1. So that's why the sum of this series is 1. So you can easily understand it geometrically.